Hello. Today we'll be talking about equilibrium and statics. Equilibrium being a balance of influences, and statics being the study of things that don't move. First, let's talk about equilibrium. This is the condition in a system, again, where competing influences are balanced against each other. And we talked about forces, we'll talk about moments today, but equilibrium describes a condition then when there is no net force on an object and there is no net moment acting on an object. So we know all about forces. To say that there's no net force means that there's no net acceleration of the object, because remember that F net equals mass times acceleration. If there's no net force, there's either no mass or no acceleration, and assuming this is a real object, then the mass will not be zero, thus the acceleration will be zero. Now you should note that this state of equilibrium does not mean that there are no forces acting on a body or an object, or that it's not moving. Those two things might be true, but aren't necessarily true. What is necessarily true is that any forces that do act are balanced. And so Newton's first law tells us that without a net force, without net external force acting on an object, it will tend to stay in its state of motion, whatever it's in. That means that if it's stationary, it'll stay stationary. If it's moving, it'll stay moving at that same velocity in that same direction. And thus, in the absence of unbalanced forces, this object will not be accelerating. There are two kinds of equilibrium that we'll be talking about today. The first being translational equilibrium, which is to say that there's no net force acting on an object to make it move in a line or translate through space. The second part is rotational equilibrium, which says that there are no force acting on a body such that it will make the body turn. And so, if we imagine some sort of elongated object with its center of mass right here, if there was a force acting right here on the center of mass, this object would move in this direction. But if this force was not acting on the center of mass, say it was right here, then this object may rotate depending on how much friction it's experiencing on the surface it's resting on, but it will also tend to rotate. And so this force will cause the object to rotate. And so a state of equilibrium suggests that there is no net force acting to make the object translate through space, and no force that is acting to make it rotate. And when an object has both of these kinds of equilibrium, satisfies both of these conditions, we can say that it's in static equilibrium, that is to say it's not moving. Let's take a look at this object system. In this case, we have a fulcrum and a beam resting on the fulcrum. There's a mass on one side of the fulcrum, and that mass is being held up by the fact that someone is pushing down on this end of the beam. In this case, the beam itself does not have a mass. If it did, then there would be some F over here at the center, which acts at the center of mass of the beam. That's not the case today, so that is left out. We should note that in this situation we have on the beam, let's look at the beam, a force down due to this mass being here. So this is pulling the beam down. This force here, which is holding this mass up off the ground, is also acting downward on this beam. So there are two forces pushing downward on the beam. And yet, we're going to assume that this is a stationary situation. If that's true, then this beam is not accelerating into the ground. So there must be some force balancing those other two forces to keep it from accelerating into the ground, and that comes from the fulcrum. This force Ff coming up from the fulcrum balances these two downward forces to keep everything in place. It's not accelerating off the ground, so there's no net force up. It's not accelerating into the ground. These two forces then must balance this one force here. Also, if we think about what happens, let's say we removed F2. This is a stationary situation. Everything's just hanging out in place, and we removed F2. What would happen to this beam? It would rotate about this point. Rotate right there. Right here. This force, due to the mass, would cause the beam to rotate this way. And so, if that's not happening, that means that the clockwise motion, which would be caused by F2 in the absence of F1, and the counterclockwise motion, which would be caused by F1 if F2 weren't there, those two rotational moments, they're called, those two rotational tendencies are balanced, and we're also in a state of rotational equilibrium.